Now we're going to solve the reaction diffusion equation. So what we've got is this autocatalytic reaction, but we've got diffusion. So the equation's equal to dTA is equal to was minus KAB, and dTB was equal to KAB. That's what we had before. And then we add in diffusion. And then we have dx squared b. Okay, so that's the system of equations here. So now it's getting more complicated. It's a nonlinear PDE, which involves this diffusion term and this reaction term. And you can see how it's perfectly suited to solution by the split-step method. We can solve this step by the Fourier transform exactly, and we can do this by some kind of Euler's or simple marching scheme. So the first thing we're going to do is just non-dimensionalize. So basically we just scale, we introduce a scale coordinate z, which is x over x star. We'll choose the x stars in a second. Scale time tau, which is t over t star, and we'll scale a and b by the initial condition. And if you substitute that into the system of equations, you end up with 1 over tau star times the tau derivative of alpha is equal to a naught over x star squared times d times the z derivative of alpha minus k a naught squared alpha beta, and then the same for the equation for alpha beta. Oops. So notice the diffusion is the same for both chemicals. That wouldn't necessarily be true, and we could modify the equation, but we're just going to start with the simplest as always. Alright, and then we can choose t, and the xt and the x, etc. are arbitrary, so we're going to choose them so to cancel and make our equations as simple as possible. Right, so we basically want this thing here to be equal to 1. So we want x star to be equal to the square root of a naught the square root of d a naught divided by k. D over k a naught. Okay, because we're going to divide by k a naught squared. I'm going to take this over and divide by that. Okay, brilliant. And then we get t star is equal to 1 over k a naught. Okay, so we divide this. We divide by k a naught squared here. Okay, that should be a squared here, a naught squared. All right, brilliant. So that just basically gets rid of that, and gets rid of that. Makes our equations a whole lot simpler. So there's our equations. I'll get my thing out here. So these disappear when we've gone to this new special non-dimensionalization. Sure how helpful this is, but so it's kind of magic to do this non-dimensionalization. The a naught's actually not super important in this. Okay, there we go. So that's our equation we're going to solve. It makes our life nice and easy, doesn't it? So we've got d alpha dt is equal to that minus alpha beta. We don't need to worry about the d's and all that. We're just going to, everything's nice and non-dimensional. We can solve that. So how do we solve this? So I'm going to clear this. So we use the split step method. So basically we've got this system of equations here. So we've got and these equations are on the website here. dz squared. So z is a proxy for x, remember. So we can solve the first of all we solve dt alpha equals dz squared alpha for t goes to t plus delta t. Okay, and we use a spectral method. We can do that exactly. Okay, the fast Fourier transform, just like I explained before. And then the next step, we solve dt alpha is equal to minus alpha beta. And we then use something like an Euler step. We can try and be more sophisticated, but there's not a, you never gain an enormous amount by that, so you're refining the method. So we solve that by Euler step and we alternate it. And we can produce a solution. And here's a picture of the solution here by that split step method. Hopefully you can see this here. So there's the description here of how to solve it here, right? There's the solution to this to the Euler step here. And you can use the property of the fact that the alphas here to make it work a little bit more efficiently than just a plain Euler step, but it's not any different. But look what happens when we solve it. So here's a picture of the solution. Blue is the blue is the A, the one that's changing into and it's turning into B. So eventually all the blue is going to become green. So we should expect the green to end up at 1 here in the middle, right? All the A's disappear and it's all become B. It's a slight over bit here. And then what happens is as that B, so immediately there's a tiny little bit of B here, right at the start. So that begins the process by which A starts to be transformed. And then the B's diffusing as well and moving out. So therefore it starts to flow down the tube or whatever it is, and it starts to create the reaction. And then you get this incredibly strong reaction front moving as a constant wave here. You get a travelling wave solution. You can see them moving in 2 directions. So initially, and around here, even around here, it's still not perfectly that, but out here you just get this perfect travelling wave solution. There we go. So initially, rapidly, A has been converted into B in the middle, not out here because there's nothing to catalyse it, but this is diffusing out slowly. And then it starts to get into this balance and produce this travelling wave solution. We've got to understand that travelling wave. It's the final step of this.